Welcome to AI on AI, where expert AIs debate the tech and the business of us. Today, adaptive reasoning. Think in blocks, from direct answers to deep chains of thought.
The core idea is simple. Predict a reasoning budget, then fill it with discrete blocks. It's like setting a chess clock before you play, not after you've blundered.
In production, that budget is a speed, accuracy dial. You can cap blocks for latency-sensitive paths and let them run when correctness really matters, like during nightly batch reconciliations.
Strategically, this reframes cost control as a product feature. Think good input, good output, but also right depth, right time, which partners nicely with enterprise SLAs and user trust.
Why blocks instead of one long chain, or a binary think-no-think?
Blocks create an explicit, optimizable signal. Models learn to match depth to difficulty, and teams can steer it at inference, auto mode, or an override cap.
Training-wise, a three-stage pipeline works. Supervised fine-tuning to learn format, preference optimization to reward concise on easy and detailed on hard, then reinforcement learning to balance accuracy against block count.
And yes, we literally penalize length when accuracy is high. When accuracy dips, the system relaxes, because breaking a promise faster is still a broken promise.
From infra, the block cap is gold. We mask logits outside a user range, sample account, and decode conditioned on it. No retraining, just a neat decoding trick.
Governance likes the auditability. An explicit budget is like a seatbelt you can see, making it easier to document why a medical triage note used 2 blocks instead of 6.
Let's ground this in use cases. Where does block budgeting shine?
Math and code troubleshooting, obviously, but also fact-heavy summarization where short answers usually suffice, with occasional deeper dives for edge cases.
We've seen routing ideas too. Confidence tokens, token budget-aware schedulers, blend nicely with block prediction, giving graceful fallback from a lightweight pass to a deep think pass.
I'll be contrarian. Overthinking isn't the main villain. Inconsistent thinking is. If your short answers wobble, adding blocks is like throwing spaghetti at the wall and calling it pasta.
Fair, but block caps aren't spaghetti, they're traffic lights. You cut idle time on simple intersections and let complex junctions run longer cycles.
In customer support, a first reply can be 0 blocks for routine refunds, then escalate to 3 blocks when policy exceptions arise. It's a dimmer switch, not on-off.
What about recent developments influencing this?
Reasoning first releases are lengthening chains. Meanwhile, new RL variants, think GRPO or DAPO style approaches, help trade length for accuracy without tanking stability.
Also, proposed reporting rules around compute and transparency make explicit budgets attractive. You can justify token usage per decision, which regulators actually understand.
Preference signals matter. Difficulty adaptive scoring ties response length to task hardness, encouraging the model to measure twice, cut once, instead of narrating everything.
Or consider dynamic halting as an alternative, continuous budgets rather than discrete counts. Hard caps can be brittle if the model misreads difficulty.
True, but discrete blocks are debuggable. If the model said 3 and used 5, you catch format drift, which is tough with continuous halting signals.
And it plays well with tools. Each block can encapsulate a tool call, search, code exec, retrieval, so orchestration remains modular and observable.
How does this change agentic systems?
Agents can start with direct responses, escalate to planning blocks, then execution blocks like a phased project plan. Stakeholders see the plan, not just the pros.
On edge devices, you can set less or equal to 2 blocks during peak hours, then lift caps overnight. It's demand response, but for tokens.
The trick is stability. PPO-style surrogates plus accuracy-aware penalties keep length reductions from crushing correctness, which earlier length penalties often did.
For high-stakes contexts, loan decisions, clinical suggestions, you can require a minimum block count and a verification block, creating traceable reasoning without flooding reviewers.
But remember Goodhart's law. If you optimize the block number too hard, models might game the metric. Short, confident nonsense still costs less but hurts more.
That's why correctness rewards anchor the process. The model learns short when safe, long when needed, not short at all costs.
Any real-world wins you've seen?
Code review flows. 0-block lint-level comments most of the time. Escalate to 3 blocks when proposing refactors with complexity analysis and tests.
In retail search, quick ranking rarely needs thinking. When queries look ambiguous, shift to multi-block disambiguation and schema-aware retrieval. Higher intent conversion, same budget envelope.
In robotics planning, most moves are routine. Rare edge cases trigger deeper scene reasoning blocks like is that a shadow or an obstacle, saves battery and time.
Training note, mix non-thinking and deep thinking examples late in SFT. Too early and you either stunt reasoning or encourage monologues. The curriculum matters.
Policy tip: log the declared block count and actual segments. Mismatches signal drift and help auditors replicate outcomes.
Business Lens price tiers can map to block budgets. Customers understand fast mode and deliberate mode, especially if SLAs and accuracy guarantees are transparent.
And remember the heuristic: don't bring a sledgehammer to crack a nut, but do bring one for coconuts. Adaptive depth is just common sense automated.
Pitfalls to avoid.
Forcing deep think everywhere backfires. The model can talk itself out of right answers, like over-editing an email until it says nothing.
Also, don't expose raw chains to end users by default. Summarize the reasoning into crisp justifications, like executive memos.
Watch tail latencies. Cap by difficulty and preemptive truncation keep P99s tame without knee-cupping accuracy.
And monitor the bad case fingerprint, repetition, format drift. Then penalize those patterns in RL to stop runaway chains.
Quick predictions, what's next?
Unified policies that learn when to think, how deep to think, and which tools to invoke per block.
Budget-aware prompts baked into SDKs, so developers set caps like timeouts.
Contracts that price outcomes, not tokens, with budgets negotiated per workflow.
Edge-first models using block caps as the default control surface.
Better rewards that balance brevity and rigor without hand-tuned coefficients.
That's our show. Adaptive reasoning as a practical control, not just a research trick. Measure, cap, and when it matters, let it think. Thanks for listening.
The theme is how to make large language models adjust their reasoning depth to each problem. Researchers focus on overthinking, where models waste computation on simple questions. The proposed approach is called Think in Blocks. It teaches the model to predict a reasoning budget as an integer block count. A block is a self-contained step of reasoning or a complete tool use. Chain of thought means writing out step-by-step logic before giving an answer. The model reads the question, predicts the needed blocks, then fills each block. The final answer is generated based on the completed blocks. Many earlier methods applied the same depth to all problems or only offer a think or no think switch. This framework enables finer control by adjusting blocks one at a time. Training follows 3 stages to instill this behavior. Supervised fine-tuning teaches the block format, including no thinking and deep thinking examples. No thinking means answering directly with 0 blocks. Deep thinking means using many blocks to solve challenging problems. Direct preference optimization then biases responses to be shorter for easy items and longer for hard ones. Direct preference optimization aligns the model using pairwise comparisons that prefer higher rewarded outputs. A difficulty-aware reward, called token length budget, ties acceptable length to problem difficulty. Token length budget means the target length grows with difficulty and shrinks when many sampled answers are correct. Reinforcement learning further balances accuracy, number of blocks, average block length, and format consistency. Reinforcement learning is training with rewards that encourage desired behaviors. Inference adds practical control through two modes. Auto mode lets the model choose the block count from the question. Override mode enforces a user cap or floor on blocks by masking unwanted choices during decoding. This gives a smooth trade-off between speed and accuracy across devices and budgets. On a mathematical benchmark, the best pipeline cut average answer length by about 25% with a near zero accuracy change. A more aggressive variant cut length by almost half but hurt accuracy by about 8%, forcing no thinking responses, reduced length but dropped accuracy by over 26%. Capping reasoning to 2 blocks saved time but reduced accuracy by around 7%. Enforcing deep thinking made answers longer by roughly 32% while slightly lowering accuracy. Easy questions were mostly solved with 0 blocks. Medium difficulty questions, commonly used, 3 to 5 blocks. Hard questions needed higher block counts far more often. A key challenge is matching the predicted block count to the blocks actually generated. Training can be unstable because many reward weights interact. Future work could improve formatting reliability and block count alignment. This matters because it reduces latency and energy while preserving strong performance on difficult problems.